All right, so today we are doing section 4.4, which is graphing a function rule. The set of all solutions of an equation forms the equation's graph. A graph may include solutions that do not appear in the table. So all this is saying is just because you see 4 ordered pairs here once we fill this table out, that does not mean that there are only 4 ordered pairs in the graph. Right? There's actually an infinite amount of ordered pairs that are found in the graph when it comes to graphing a line. But we only need to do about 3 or 4 of them here so that we get a general idea of what the picture or what the graph is going to look like. So they give me an equation, also known as a function, and they give me values of x. We have to plug those values of x into our equation. So the first one, y equals -2 times -1 plus 1. Again, I'm just replacing the x with -1. When you simplify that, you get 3. So that is the y value. That means your ordered pair is -1, comma 3. Okay, keep in mind ordered pairs always go x, comma y. They go in alphabetical order. Okay, working with 0, plug 0 in for x now and simplify. You get +1. Create your ordered pair. Plug in +1 and simplify. You get -1. So your ordered pair is 1, -1. And then plug in +2. Simplify. You get -3. So the next step here is to graph these ordered pairs. So keeping in mind that this here is our x-axis, this is our y-axis. If we graph the first ordered pair, -1, comma 3, that means we go over to -1 on the x-axis and then you go up 3. That is your ordered pair. The blue one, we go to 0 on the x-axis, so there is no movement on the horizontal axis. However, you do go up 1 on the y-axis. 1, -1, and then 2, comma 3. So looking at the next example here, and we can connect these ordered pairs since we know it's a line. We actually talked about this in 4.2 to 4.3 about discrete and continuous. So for these ones, we can go ahead and connect those lines. Another word you may hear for x is called an input. So think about it, you're inputting numbers in for x. And the output is considered the y value. So whatever you input, what is your output? I always think of it as a machine, right? You're inputting something and it ends up giving you a value at the end. So looking at our equation, y equals 1/2 x minus 1. I would be a little bit strategic here with the values that you pick for x. Because we're working with a fraction, it will make your life a lot easier if you pick values that are divisible by 2. Okay, you don't have to. It's not wrong if you don't. However, good rule of thumb for this is to pick values that are divisible by 2. So for example, if I pick -4, right? 1/2 times -4, well, that's just -2. And then -1 would give you -3. I'm going to go ahead and pick -2, pick 0, pick 2, and pick 4. So we usually always try and do 2 negatives, meaning pick 2 negative x values, always do 0, and then pick 2 positives. So if I go ahead and pick or use -4 and plug it in, I would get 1/2 times -4 minus 1, which gives me -3. Okay, so my ordered pair is -4, comma -3. If I do -2, again, plug it in, make your ordered pair. Once you have your ordered pairs, then you're going to graph. So if I graph this first one, -4, -3, it's going to go here. -2, -2, 0, -1, 2, 0, and then 4, 1. All right, flipping to the next page here, it says that whenever you graph a real-world function rule, choose appropriate intervals for the units on the axis. Every interval on an axis should represent the same change in value. If all data are non-negative, show only the first quadrant. So what that's saying is if you have values that are only positive, no negatives, it's going to stay in this first quadrant. So this is the first, second, third, fourth. Okay, the other part of it, whenever they're talking about the interval on the axis, they're just saying, like if you notice in this example, every block had a value of 1. Okay, and I suggest doing the same scale for the x and the y because when we get to chapter 5, it will really help out with slope. But you are allowed to have a different scale for the x-axis than you do for the y. You just have to be careful because you cannot do something like this. If you let that be 1, this be 2, you can't jump up to 5 and then go to 6, right? Because that has a change of 3 versus the change of 1. So that's all that first part's saying. So the function rule W equals 146C plus 30,000 represents the total weight in pounds of a concrete mixer truck that carries C cubic feet of concrete. If the capacity of the truck is about 200 feet cubed, what is a reasonable graph of the function rule? So if you think about this, what values of C would be reasonable? So C was the concrete. So if you're thinking of some amount of concrete, right, it doesn't make sense to be in the negative, so we'd want to start with 0, right? And then if it can only hold about 200 feet cubed of concrete, that means that it can only be a maximum of 200. So it would be reasonable for C to go all the way up to 200. Now, whenever we're trying to graph this, okay, let's go ahead and label. So this would be concrete, right? Because the amount of concrete is going to affect the total weight. Now, because we're doing a scale of 0 to 0 to 200, we have to think about what each block needs to represent. If we do tens, we're not going to reach 200, right? We're trying to see as much of this graph as we can. If we do 20, I think it might be cutting it close. You may be able to get to 200. I'm going to actually do 25s. Okay, that way I get a good view of what exactly this is going to look like. So go ahead and start labeling. Now for total weight, this is what I was talking about before. It doesn't make sense for the y scale to go by 25s because if you look at this equation, right, if we have 0 concrete in our truck, right, it's still going to have a weight of 30,000 just because of the truck itself. So if we only go up by 50s on here, 25s, there's no way we're going to actually be able to see any of the graph. So thinking about this, because this value here is so high, I'm going to hold off on making my y scale. I'm going to go ahead and take some values for concrete and find what the W is. So I'm going to go ahead and do, now it doesn't make sense to do negatives, right? We just talked about that. So I'm going to start with 0, and then I'm going to go ahead and go up by 50. That way I only have to graph about 5 points, and it will give me the majority of my graph, if not all of it. So at this point, you're taking these values of C and you're plugging them in for that C. So go ahead, you can pause me if you want while you work through this. Make sure you're able to plug these values in, please. Oops. So looking at the table now, we are going to, let's see, it probably makes sense if we go up by 10,000. Right, and the reason I'm getting that is because my first is going to be 30,000. I don't want to go up by 30,000 because that means all of those points, we'd be cramming them together. We want to spread it out some. So if I go up by 10,000, this is where you have to write kind of small here. I'm going to go ahead and graph my points. So again, this point here would be 0, 30,000, 50, 37,000, 7,300, 100, 44,000, 600, 150, 51,900, 200, 59. All right, so graphing these points, 50 up to 37, you are going to have to estimate a little bit, no big deal. A 100 up to 44, so about here. 150 up to 51.9, and then 200 up to 50. Oops. There you go. All right, so there is our graph. So what is the weight of the truck when it's empty? So that's whenever there's no concrete in it, and that's that 30,000 pounds. Okay, remember we got that first from our table, but also from this equation. And we can actually connect these. All right. Okay, I'm sorry, we're doing continuous and discrete here, not in 4.2 to 4.3. Okay, even better. So, two different types of graphs. We have something called a continuous graph and something called a discrete graph. So if you think about it, continuous means it's unbroken, right? It continues to go. So the way I think about it is if it's continuous, you don't have to pick up your pencil to get to the next value. Right? So if you're following this line, you can follow the entire line without picking up your pencil after you place it. Discrete, however, you have to pick up the pencil to get to the next value, right? So for example, if I'm starting here, I can't just continue to go, right? They're not connected. So instead, I have to pick up my pencil. Okay, so it says a discrete graph is composed of distinct isolated points. All right, so if we take a look at this first example, describe if it is continuous or discrete and justify. So the amount of water in a wading pool in gallons depends on the amount of time in minutes the wading pool has been filling, as related to the function W equals 3t. So t is time, right? W is the amount of water. So I'm going to fill in my table first, just taking these values for y, plugging them into my equation for t, taking the values of t, plugging them into my equation for t. So 3, 6, 9, 12. When I graph those, This is where you don't want to automatically connect the points. So don't connect points yet. Okay, you have to think about it. Is it continuous, right? Meaning, yes, those are the 4 points that we found, but is there such thing as having maybe 1.5 minutes or 2.5 minutes or 3.5 minutes, right? Yes, that does exist. You can have any amount of gallons and any amount of time as you need. So yes, we would connect, okay, because you can have any amount of water, right? So for example, after 1.5 minutes, if you plug 1.5 in for T, you would get 4.5 gallons. It makes sense to have half a gallon, right? You can have half gallons, quarter gallons, third gallons. So in that case, it would be continuous. If you look at one like number 5, you're buying baseball tickets. Okay, so here is our equation. Okay, if I'm buying tickets, I can't buy negative tickets, so it doesn't make sense to start with negatives when I make my table. Instead, I'm going to start with 0 and go ahead and do 1, 2, and 3. When you plug those in, you get 0, 16, 32, 48. Okay, so this is tickets, number of tickets. This would be cost. 1 ticket, 2, 3, 4, 5, and so on. Cost, let's see, looks like it goes up by 16, but just to spread it out a little more, I'm going to go ahead and go up by 8. And then when I graph, 1 to 16, 2 to 32, 3 to 48. This is where you want to think about it. Okay, does it make sense to connect the dots, right, the ordered pairs? Is there some amount of tickets that you can buy 1.5 tickets, right? No, you cannot. So this would be discrete. You can only have a whole number of tickets, right? You can't buy half tickets. So you would just leave it like that without connecting the ordered pairs. All right, so let's look at the last 3 graphs that we have here. When you look at 6, 7, and 8, if you notice, they do not look like our usual equations we've been working with, right? That has an absolute value. That has an exponent of 2. This has an exponent of 3. So these are 3 new types of equations that we're going to learn, more so just the graphs of them. So this is called an absolute value equation. This is called a quadratic, and you will learn about those in Algebra 2. And this is called a cubic. Our goal is to pick enough points to show the graph. Okay, so with these problems, again, like I did on that front page, I would always pick 2 negatives, 0, and then 2 positives. Okay, so if I go ahead and pick, I'm just going to go ahead and pick -4, -2, 0, 2, and 4. It would not be wrong if you went with -2, -1, 0, 1, and 2. That's fine. I'm just trying to show majority of the graph here. Okay? Sometimes whenever you pick ordered pairs, you actually have to start over because you notice that it doesn't give you the graph, the entire graph, or it doesn't show you enough. So when we put -4 in for the absolute value of -4 minus 4, that's going to give you 0. absolute value of -2, and then -4 is going to give you -2. Continue to plug in your points, and then graph. So -4, 0, -2, -2, 0, -4, 2, -2, and then 4, 0. And we will connect here. We're not working with any scenarios here, so we're safe to connect. So if you notice, it makes a V. All right, so anytime you do an absolute value, it will always make a V. Now, sometimes it could be an upside down V, though. One thing to note, if we would have skipped these negative values here, we would have only had the right side of the graph, right? And that would have looked exactly like a line. You would have probably thought, hey, look, it's linear, it's just a line. So that's why we want to make sure we pick those negatives to see both sides. Okay, now when we do number 7, same idea. I'm going to go ahead and pick some negative values. I'm just going to do the same, -4, -2, 0, 2, and 4. When you take -4 and you plug it in for x, please be very careful. It needs to go into parentheses when you square it. Okay, because again, guys, remember, -4 squared is -16. -4 in parentheses squared is +16. Okay, so this here would go to 12. This would go to 0. This would go to -4, 0, 12. So when we go to graph these, -4, 12, that falls off our graph, but that's okay. All right, so it's just going to be somewhere up here. -2 zeros right here. 0, -4, 2, 0, and then 4, 12. Okay, so the way this shape, or this graph, it is actually a U. It's called a parabola. Okay, so you want to be careful you don't make it into a V. It's actually a U. And again, they can be U's or they can be upside down U's. All right, last one here. I'm just going to go ahead and do, I don't want to start with -4 because if you cube -4, you're going to get -64, and I really don't feel like graphing something that has a y value of -64. Okay, so, and that'd actually be -63 after you add 1. So we're going to do -2, -1, 0, 1, and 2. When you plug these in, again, you need to hug this with parentheses. -2 cubed plus 1, that's going to give you -7. -1 cubed plus 1 will give you 0. 0 cubed plus 1 is 1. 1 cubed plus 1 is 2. 2 cubed plus 1 is 9. So graphing these, we have a point here. -1, 0, 0, 1, 1, 2, 2 up to 9. So the way this graph looks is we have a curve here, and then a curve going down, and then to the top. Okay, so one more time. Let me draw that for you again. Oh, sorry guys. So a curve, and then a curve. All right, so now if you ever have to graph on the test, you want to make sure you recognize, hey, this is an absolute value. I should be thinking of a V or an upside down V. Hey, this is a quadratic because of the 2, the squared. I should be seeing something like this or something like this. Hey, this is a cubic. It's going to be something like that. Oh, that's pretty messy. All right. So what you need to do now is